Vamos. Buenas tardes. Good afternoon. Thank you for coming to this talk. I will start by thanking the conference chairs for the conference on nonlinear science and complexity, Professor Cristor Bolos, Professor Eftimia Meletiau, and organizer Jamil Odiseaus Maita from the Thessalonian University in Greece, and Professors Jesus Manuel Muñoz Pacheco y Ernesto Zambrano Serrano, organizers of the symposium number 10 on chaos behavior and synchronization in fractional and integer order chaotic systems. My name is Juan Gonzalo Barajas Ramirez. I come from EPC in Mexico, and I will give the talk, Synchronization of Chaotic Systems with Different Attractors. The outline of my talk is as follows. I will start by introducing anti-control of chaos, then the synchronization problem in two configurations, the drive response and the bidirectional coupling configurations, and we'll give some results and close the talk with some closing remarks. Anti-control of chaos basically means to have a stable linear time invariant system, and by adding a control signal, making it chaotic. In particular, we propose a methodology relatively well known to generate multi-scroll attractors in chaotic systems using linear commuted control, which is basically defined for different parts of the state space, a different controller that basically just makes the system jump from one eigen direction and eigen line and eigen plane to another with a different location of the scroll, and it generates a set of scrolls wherever you decide to place the equilibrium points. In closed loop, our system has a very simple linear affine description that is valid for each partition of the state space. In each partition, you have an equilibrium point given very easily from that equation. And then you need to describe K and F such that chaotic dynamics are generated with multi-scrolls. In particular, we will consider 3 domains, and we will use a dynamical system that has the simple structure given here, right? A real, negative real eigenvalue and a complex conjugate with a real part. In this way, you have a stable direction and an unstable plane invariant. In this case, we choose the location of the parameters as given here, so that you will have a stable eigen direction or eigen line associated with a real eigenvalue alpha, and an eigen plane that is unstable, where you have a beta as the real part of the eigenvalue and gamma as the complex conjugate value. In this way, you can place, for example, the equilibrium points at the origin, and one negative and one positive. Adding the switching planes proposed here, you'll describe a simple transition between the stable and unstable directions of this local linear dynamics. That is, you will generate an attractor with 3 scrolls as proposed here, with a simple geometry as shown in this slide. You'll have the pale blue as the stable directions of the eigenlines that go from one equilibrium point from one unstable eigendirection, the plane, to the equilibrium point, and the pale green is the unstable planes where the scrolls are generated. The transition between one and the other are designed such that when the unstable direction grows sufficiently large, switches to the stable direction, then it takes the unstable direction towards the stable, then switches and goes towards the stable, and the unstable makes it return on the other side, right? So you'll have an heteroclinic cycle for the generation of attractors. Okay, in the case of three equilibrium and three equilibrium points and three dynamical components, you have this. Then you'll have the same for 4. So we have 2 different systems with different attractors, and we will try to couple them together. First, we couple them in a dry response configuration, and then in a bidirectional configuration. In the case of a dry response configuration, you need only to design the coupling gain K and the affine component E. In this case, a simple Lyapunov function can be used to determine the stability of the aerodynamics, and you will have synchronization. In particular, in the case of 3 nodes, 3 scrolls connected to a 4 scroll, you will force the 4 scroll system to synchronize to a 3 scroll. So he will forget one of the scrolls. In a remark that I need to make about the type of coupling here is that the coupling is fixed. So it doesn't switch with different types of, with different locations on the state space. This is possible because the the generating dynamics matrices A plus K are identical, even though the F's are different, right? Simply it forgets the last scroll once it's synchronized. For the bidirectional coupling, the problem becomes a little more complex because both systems are changing. However, you can still find the aerodynamics and conditions under which this aerodynamic is stable, and you can force again the 4-dimensional and the 3-dimensional to live as a 3-dimensional system. As a 3-scroll system, I'm sorry, 3 scroll systems. And the error has small changes or additional errors when you switch between one domain and the other, because again, here we are using a controller that doesn't change, it's fixed. Okay, so what we are working on is to investigate the synchronization in chaotic systems with different number of scrolls. Yet the distribution is very similar. In this particular case, even the matrix that generates the oscillating dynamics is the same. However, we observed that in the drive response synchronization configuration, synchronization is achieved towards the attractor with the less number of scrolls. Potentially, we can force the other system to follow the one with the largest number of scrolls, but we haven't. We feel that with a fixed controller or chaotifying or coupling controller is not. We cannot achieve it as well. In the case of the bidirectional configuration, we consider that we have a a sufficiently good result yet. For future work, we will make a switching control law for the coupling such that at each location and depending on the error size, you will have a different controller. For future work, we are working on trying to solve the problem of especially bidirectional synchronization when both the A's and the F's are different. This type of synchronization is usually called itinerary synchronization. Okay, I will stop here. I hope that I can have questions from you so I can answer them. I will again like to thank the organizers and the symposium organizers. I am available for questions at this address, email jgbarajas@epc.edu.mx. And please, if you have any questions, please let me know. Thank you very much again. And I think my time is up. Thank you.